All right. So we started by saying the paper by Susskind, right? Essentially, we were talking about the paper by Susskind. That he argued that there should be no fundamental scalars. So let's look into this argument. Why he mentioned that there should not be any more fundamental scalars. So his argument stems from, okay, so his argument stems from talking to Wilson, essentially. So what is this argument? His argument stands from something called Wilsonian effective field theory. So what is this Wilsonian effective field theory? Okay, so what Wilsonian effective field theory is that, okay, so you can write it formally. I think we should switch on the lights. If you write formally L effective, so you can derive an effective field theory. Do you want to switch on the AC or something? It's already hot, right? Actually, yeah. So you define an effective field theory based on a momentum cutoff, essentially, based on a cutoff, essentially. So L effective would be integral. It's a path integral, essentially, of all the fields e power I s L. Okay. Now this cutoff is that you make these modes, all the field modes, dependent on, you only integrate out all the modes above the cutoff completely and derive what is a lower energy mode. Okay, you integrate out, remove all the modes which are heavier than momentum modes, which are heavier than lambda, and you derive only the effect of what is left here. Now in this case, what happens is, if you do that, okay, now let's apply this to standard model, essentially. Apply it to standard model. Now in standard model, what you have is LSM will have L gauge or L kinetic plus L Yukawa plus L scalar L fermion is the kinetic, essentially. L gauge part, essentially. This is the gauge kinetic terms. The scalar part, Yukawa, and now all the masses, everything. I started early today. Sorry, okay, I had to go early. So, yeah. So, what we are talking about is what is the Wilsonian effective field theory. Okay, we were talking about Suskind's paper, right? Essentially. So, which starts with saying that there are no fundamental scalars in the universe. That's the argument he tries to give. Okay, why his argument comes is the question, essentially. So, there is something called an effective theory called Wilsonian effective field theory. Wilsonian you know effective field theories, right? Okay. So this is Wilsonian effective theory. It gives a physical interpretation of the entire renormalization scheme. So you say that you derive an effective field theory by integrating out momentum modes which are heavier than some physical scale lambda. So you remove all the momentum modes. So all the fields will have which have momentum modes heavier than lambda. You integrate them completely essentially. So and remaining part you call as an effective Lagrangian, and this is called Wilsonian RG. If you want to talk to any condensed matter person or something, he says that the physics below this physical cutoff is determined by the cell effective. The physics below this cutoff is this is called Wilson RG. You can also derive an RG equation by taking two cutoffs and then comparing them essentially. This procedure can be done essentially. You can do this entirely not only in cutoff method, but okay, let's stick to cutoff method essentially. I'll tell you examples how you can do it without cutoff method also. This same arguments holds. Now apply it to standard model. Now standard model has kinetic terms for the fermions, Ikawa couplings, scalars, and the gauge kinetic terms essentially. Okay, so now if you see this, what it looks like, all of them have some symmetries which protect them. We discussed this essentially. So we said there are chiral symmetries which protect the fermion masses, which are nothing but the flavor symmetries which we talked about. Okay, so what it means that all particle masses are protected by some symmetry. What does it mean by that? Essentially, all particle masses are protected by some symmetry. Now, if I set this is also goes sometimes attributed to 2. If we set some parameter to 0 in the theory, the theory should have an enhanced symmetry. Okay. If one sets a parameter to 0, the theory should have an enhanced symmetry. Now, if you set, let's look into the masses of this one. We're really interested in the masses because, okay. So, suppose if we set the quark masses to 0, okay, so you have enhanced flavor symmetries, or which are also called chiral symmetries because the left symmetry and the right symmetry exist. Okay, the left symmetry and the right symmetry exist. So quark masses or lepton masses, these are all the properties which we have seen in the first classes or something, if you remember. Okay, there was enhanced. So new symmetries which appear are flavor symmetries, which are chiral in nature. Why? You say the flavor symmetry has SU3Q, sorry, SU3Q and then SU3U U and then SU3D. You can rotate independently the left part and the right part. Okay, so if you set the Ikawa coupling to 0, there is nothing in the standard model which can distinguish between the generations. Okay, if you set the equal couplings to 0, that means if you set all the masses to 0, there is nothing which you can distinguish anything, meaning you cannot say what is an up quark or a down quark, what is the difference between up quark or say charm quark or a top quark. But the symmetry is chiral because all the left fields, because SU2 symmetry is chiral, all the left fields have a different rotation, all the right fields have different rotation, all the right fields down sector have a different rotation because they have different quantum numbers under U1 essentially. Okay, so sometimes these are also called chiral symmetries. So if you set Yukawa couplings to 0, there is an enhanced chiral symmetry. So this chiral symmetry protects the masses of fermions. The masses of fermions are protected by the chiral symmetry. Now if I set gauge boson masses to 0, pardon? You cannot write any mass number. No, as of now we are spontaneously symmetry breaking, right? Okay. Yeah, so spontaneously if you set it to 0, there is a symmetry which protects it. So what it means, what symmetry tells you is that if this symmetry is protected, that means radiative to corrections to masses are protected by symmetries, means chiral symmetries are broken by Yukawa couplings. So every radiative correction to, that's a good question, I missed this point. So if you have a ME radiative correction, this will always be proportional to ME. So if you set this to 0, the radiative correction also go to 0. You cannot generate dynamically. That's what symmetry tells you. So you cannot generate it radiatively. The mass cannot be generated radiatively because the symmetry is protected. Okay. Now same thing if you set, okay, so the other words are essentially that radiative corrections to fermion masses are proportional to themselves. Now this you can see easily. Now let's try to draw a Feynman diagram. Okay, so you start with say electron mass, right? We are talking about electron mass, some photon. You need to put this mass of the electron on the fermion propagator, on the fermion line. Instead of this, you put in W. Okay, it will always be proportional to again EL/ER because the mass term is EL times ER. So it will always be proportional to itself, any radiative correction. Instead of gamma, you can put W, you can put Z, whatever you want essentially. So only these fields will change what comes here. If you put a W, it will be neutrino fields. If you put a Z or gamma, it will be themselves essentially. Okay. So I'll come to the dynamical generation of masses later on. I'll come, meaning that is if there is no symmetry to protect it, then you can generate dynamical. Okay, then you can generate dynamical. If there is a symmetry to protect, this mechanism works that way, that the radiative correction itself is proportional to itself. So what happens to gauge boson masses? So gauge boson masses Okay. You can think of all the vacuum diagrams and everything. So will it give you masses essentially? So what protects this? This is protected by gauge symmetry. Gauge symmetry. The limit gauge symmetry is not broken. Gauge boson masses will not get a mass. So all the masses will be proportional, radiative corrections, everything. V is web essentially. So it's some G square, V square will be there. So both of them get masses, fermions and gauge bosons get masses only after the gauge symmetry is broken. Sp2 cross. What about the Higgs? Is there any symmetry to protect the Higgs mass? Okay, can you think of some symmetry at least? So there is one more particle left, which is a scalar particle. This is a vector, that is a fermion. This is a scalar particle. No symmetry to protect it. Okay, so we set Higgs mass to 0 at tree level. Then it gets generated radiatively. How much it will be generated? In Wilsonian effective field theory, the cutoff delta amps okay, will be proportional to some 1 by 16 pi square cutoff. It takes the highest value possible. Because there is no symmetry breaking, nothing, no scale, any other scale in the theory. There is only one scale in the theory, which is the cutoff scale. So you put the cutoff scale. You don't have any other parameter. So it will only take the parameter which is the highest. So if you set it to 0, radiative corrections will drive, even if you don't set it to 0 also. Okay, radiative, because there is no symmetry protecting the Higgs mass, radiative corrections will drive the Higgs mass to infinity, to cutoff scale essentially. Question number 1. Can't we choose the cutoff small? But cutoff should be the scale at which new physics should appear. Okay, we don't know what the cutoff scale. Is there a guarantee what should be the cutoff? If there is no cutoff, what has happened? Meaning standard model is the end. Is there such a truth? There is no cutoff. Why? Pardon? No, that's fine. But suppose if these are all trivial, they can be explained locally. Say, for example, so you can, with minimal extension of standard model, you can put a dark matter particle, you can put an axion, nothing. Okay, and you can put in some neutrino masses, stuff like that. So, is there a fundamental scale beyond standard model scale? Planck scale. Planck scale. You can never cannot avoid Planck scale. So there is a fundamental scale. We know that it exists because at the scale at which the quantum gravity effect should be important. So you cannot say that You don't have a fundamental scale beyond standard model scale. So there always exists a fundamental scale. So you can put. So the Higgs mass is driven off to m Planck square. If the Higgs mass, if I put it to be m Planck, will there be electroweak symmetry breaking? No, because you won't get a wave. Okay, you need a lambda to be extremely very large essentially to get a Higgs mass, the wave to be of the same order essentially. Okay, so what is the wave formula? Wave is nothing but minus mh square by lambda. Right? So if the Higgs mass is m Planck square, lambda should be so large that the wave is 200 GeV or 100 GeV, whatever it is. Okay. So this is the conundrum. This is the conundrum, one of the conundrums, which was introduced by Susskind. So Susskind said that suppose, okay, if there is a radiative correction, let's say that there is a radiative correction very large at the level of Planck scale. Then I say that I cancel it with some counter term because radiative corrections has to be cancelled by some, it's an infinity, I'll cancel it with counter term. But the cancellation of the counter term okay should be so precise such that it gives you, so physical Higgs mass m0 square, the bare Higgs plus radiative correction. So this is m0 square plus 10 power 38 GeV square, because this goes as m Planck square. So these two should cancel, such large numbers should cancel to give you 100 GeV. How many orders of cancellation you require? You see? Okay. Okay. So 100 GeV square, if you want to get, you need a cancellation which is so precise. And this was the first thing which we encountered, argument which he mentioned as a fine tuning. Fine tuning means you have to really cancel two large numbers with very high precision to give you a small number. Okay, there 100 GeV. About 100 GeV square. Okay. So in a way, this became something called the hierarchy of the forces. Why the weak interactions are very weak, meaning are having a scale which is very small compared to gravitational force. Why the gravitational force is so weak, but it has consequences, okay, for at the quantum mechanical level, essentially meaning radiative corrections level, to weak interaction theory, essentially, to weak interactions or strong interactions at standard model scale, essentially. So standard model contains strong, weak, and electromagnetism, all the three forces, whereas gravity sits very far away. But this large separation has consequences quantum mechanically if you have a fundamental scalar in your theory. That's the point. If one has a fundamental scalar in your theory, Now this is a conundrum. So if we have a fundamental scalar, quantum gravity effects would lead to effects. Quantum gravity scale would lead to effects at the weak scale. But this goes completely against the philosophy of Wilson. What Wilson says, physics changes at every scale. So this scale should not talk to the physics at another scale. Okay, so why should, because you integrated out all the quantum gravity effects, so it should decouple off, but you are still seeing some effects, so this should not happen. So you reverse the argument and say that there is no fundamental scalars in your thing. Okay, because that's what I showed you. This is the weak scale mass, this is the effect essentially. It's fine tuning. Either you have effects or you introduce fine tuning. You have choice. Either you live with the effects, push the mass to be extremely high, or you live with fine tuning. Now fine tuning, okay, why, I mean, you can argue this about fine tuning. Two large numbers should not cancel to give a small number. There is a paper by Dirac, which some physicists don't trust, some physicists trust, called theory of the large numbers. Okay, he also talks about that there should not be unnatural ratios between in parameters of fundamental constants in your theory. So theory of large numbers, you cannot have some things which is, you cannot have cancellations between two large numbers giving you a very small number. Okay, so there are various things he talks about fundamental parameters, but philosophically this is also very similar to that essentially. Okay, there is so you shouldn't have large numbers, should not give you a small natural number. This is called unnatural. Such a thing is called unnatural. You can read this paper. This is available actually. It's not a very big paper. Okay. He brings out coincidences and everything. Okay. Now, are you convinced that there should not be any fundamental scalars? You are convinced completely. Okay. 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 Now you say that, okay, I don't believe in Wilsonian program at all. Okay, I don't believe in cutoff. Okay. Huh? You are not fully convinced. What is your issue essentially?
If there exists a fundamental scale,
Hmm.
then we will have some effects at the weak scale.
Yeah, the point is that it the effects of the Planck mass at the weak scale. That's the point. You should not see physics at a different scale. So suppose if you are looking at atomic scale physics, okay, you don't expect to see anything at the classical level. Okay, a bus moving or something, I don't know, you won't be able to do with atoms. Okay, okay, you cannot calculate with some 100,000 atoms going in a uniform. That is not the way you could. Okay, so that's a completely different physics. Okay, similarly at every scale, say for example at the atomic scale, then if you come to quark level, you don't think about the atomic system at all. Essentially, you don't care about atomic interactions, you don't care about everything. You're looking at high energy collisions, and you're looking at really protons and electron photons at those levels essentially. Okay, so the physics is changing depending upon the scale you have. So if you have many body physics also, this is much more simple. So physics changes with the scale you are considering. Okay, if you are considering a ferromagnet, it shows it at some scale, but your degrees of freedom are completely different at that scale. But if you move to a much larger scale, your degrees of freedom are completely different quantities. You don't use okay, phonons and electrons and everything essentially. Okay, yeah, now Planck scale physics should not affect anything in standard model. No, I didn't set anything. I only said that cutoff, is there a fundamental scale? I asked a question that I said there is a fundamental scale. I only said that this is sensitive to the fundamental scale. This is sensitive to the fundamental scale. It should not be, because there is no symmetry which protects it. If there is a symmetry which protects it, it is not sensitive to the fundamental scale. If there is a symmetry which protects the Higgs mass, it won't be what do you call, sensitive to the fundamental scale. It should not be cutoff sensitive. That's the main point. Physics should not be cutoff sensitive. If it is cutoff sensitive, then it's not an observable in real sense. Lowest, meaning whatever scales which comes, the first scale it hits. Because at that scale, new physics will take over, new particles will come, new degrees of freedom will come. Planck and L2, there could be some scale, but we don't know. But we know definitely that there is Planck scale. Okay, we can theorize a new scale between weak scale and we know definitely there is a weak scale, because we know GF is exist and everything essentially. But we don't know if there is a scale in between these two, Planck and this one. We definitely know there is a Planck scale. Hmm. Yeah, exactly. That you got the point. It's essentially that's the point. That you imagine that you're calculating classical physics, and you expect some fine structure constant coming into the picture. That should not happen, because fine structure constant is at a much deeper scale, at much higher scale, and you're calculating some bus going in KSRTC bus going and okay, going at a so small speed, and you're getting some effects in of say alpha EM and everything essentially. Okay, that is impossible essentially, right? Essentially, when you're calculating. So that should not happen. It's similar in the sense essentially that if you're doing some classical physics, you shouldn't expect any atomic scale physics to affect this one. Atomic scale physics is much deeper, much higher energies and everything essentially. Okay. So now you say that, okay, I don't trust completely cut off picture. Does the hierarchy problem still exist? I don't trust Wilson's picture. Can you say that? In principle, you can say that. Okay. So I say I use dimensional regularization. Okay, then there is no cutoff, there is nothing essentially. I don't have to worry about. There is no quadratic sensitivity. This is called quadratic sensitivity to the Planck mass. This is called quadratic divergences. Where does this come? You can calculate this. Okay. Okay, I'll just tell you. So for the Higgs mass, the corrections are top loop, then W loop essentially. Okay. Then you can also have Z So these kind of diagrams you can have essentially. All these diagrams are quadratically divergent. Okay, because if you look at the Feynman diagram, if you draw the Feynman diagram and give it we have done this Feynman diagram, right? Essentially, this diagram is quadratically divergent. Okay, so if you calculate this, this is P minus K, MF, P minus K minus square 3 power 4. So this, so forget about MF and everything at very large K. This just goes K square like this. You can take this part essentially, this K. Okay. Same thing happens here. All of these diagrams will have a K square sensitivity. Of course, there's a 1 by 16 pi square and everything, minus 1 by 16. So this is called quadratic divergences, and people said that if I cancel quadratic divergences, because there's no quadratic divergences in, if I use not cutoff, but if I use, say, for example, dimensional regularization, it doesn't care whether it's quadratic, log, or whatever it is. Divergence is divergence, it just puts it separately. So if I use dimensional regularization, then it should work. In standard model, you can renormalize. There's nothing stopping you. Okay, but for in that case, you don't have this problem. A scalar can exist, but it doesn't exist in the physical picture of Wilson. It doesn't exist in the physical picture of Wilsonian picture. It may not exist in the physical picture, but for all practical purposes, you can do Kalan-Zemanzik renormalization and everything. Do the dimensional regularization and calculate it, and that's how renormalization. We are looking at STU parameters and all that parameter. All of them is done in that fashion. The Higgs contribution. But if you want to give a physical picture, that there is a scale beyond standard model is valid up to this scale, and then there is some other scale which is sitting. Then if we use the Wilson energy, this creates a problem. Okay, but then there are some very nice examples given by Kaul and Mujumdar, and I think there are these simple things which were done by Kaul, which were very good. You know who is Kaul? He is our he is in our department, Ramesh Kaul. Okay, okay. Okay, there are very, very nice examples which are not very popular, but anyway, I like them very much. In the 80s, I use them in my teaching a lot. Actually, this one. So he said that let's take an example in which there is a standard model, but I have a very heavy fermion. Okay, as a standard model plus one heavy fermion, M fermion psi bar. It does. And this heavy fermion interacts with the Higgs by something. Okay, some Higgs term, Higgs or something. It gets masked with the Higgs. Then you compute the Higgs correction in this case. Okay, the Higgs correction would be use dimensional regularization. Okay, in this case, the Higgs mass correction. What is the guess? Still quadratic. It's proportional to the mass of the fermion. And so it is never proportional to itself. Higgs mass correction is never proportional to itself, that you can set it to 0, that means it remains 0 at all orders of magnitude. Okay, this was also observed by Coleman and company actually. Okay, people it was there in Coleman-Weinberg effective potential also, but within the context of hierarchy problem, this was very well explained by Cowell. Okay, I mean, people knew this, that this effect exists essentially. So there is no, even if we use dimensional regularization, the correction to the Higgs mass is always proportional to the mass of the heaviest fermion which you can couple. Now you are using dimensional regularization. There is no cutoff. Okay, even then it is very large. And so if the mass of the fermion is large, the Higgs mass also will become large. In the limit, MF is much larger than MW or weak scale, MH also will be weak scale. Again, there is a hierarchy problem. Now you cannot cancel the, because all the innovation and everything is done. There is nothing you can do here because it's dimensional regularization. So let's imagine that you have a seesaw problem, seesaw mechanism, in which there is a heavy fermion. So you say seesaw mechanism is fantastic, everything. It solves the neutrino problem. It is the ultimate. It should get Nobel Prize. Everything fine, but it has this issue because it also couples to Higgs. So in the limit, MR mass in the seesaw mechanism goes to very large, very high, which goes at the gut scale or something. The correction to the Higgs mass also becomes. How will you solve this? This becomes more acute essentially. Okay, it's time, huh? Oh, okay. Okay. I was telling him that I have to leave today because I have another meeting to go. Okay. So, so this Cowell's paper, I'll put it in the Teams page essentially. Read it. It is very good and very nice. Okay. So this tells you that hierarchy problem I'll give you another example. Okay. Independent of the regularization scheme. So if you want to use cutoff, you use it. If you want to use dimensional regularization, it's independent of the regularization. It is always there. Okay, if you have a heavy fermion, now the early assumption is beyond the standard model, there is a heavy fermion, which could appear in any grand unified theory, any seesaw mechanism, or anything. Okay, this is introducing a scale. You said, why can't I introduce a scale beyond standard model? I can introduce a scale. Okay, okay, yeah, yeah, yeah. In principle, say suppose if there is no heavy fermion exists, and there is no if there is no I use dimensional regularization. In principle, that means you are decoupling both the scales. You say that dimensional regularization, the Planck scale physics has no effect, except that you are not using Wilsonian method. Okay, the moment, but you know that there is a neutrino mass problem. You know that there is a dark matter problem. The moment you put an additional scale, the hierarchy problem will appear. Without putting a hierarchy additional scale, you won't get the hierarchy problem. You can live with the hierarchy problem. Meaning there is no real hierarchy problem in that sense. Okay, you can decouple the quantum gravity scale and standard model scale by using dimensional regularization. Okay, he's not convinced. You're convinced. Okay, all right. Okay, yeah. Okay, I will continue next week. Unfortunately, today there is afternoon. There is some meeting we heard in Rohini. I have to go there. Yeah. So I'll stop here.